Hi everyone. In this lecture we will look at alloy formation and formation of interstitial compounds in case of transition metals, right? And we'll look into the reason like why these elements, right, transition elements can form alloys and interstitial compounds. Right, we know we know iron is a transition element, right, and it can form alloys with manganese, tungsten, chromium, right? So why it can form alloys with other metals? Because we know that chromium is a transition metal, right, and manganese is also a transition metal, so they can form alloys with one another. And what is an alloy? Alloy is, if you take it's actually a solid solution. Like you have a liquid solution, you add two liquids together, mix them, right? They form a homogeneous solution which is same from top to bottom. Similarly, if you take two metals, two solids, melt them, right? When you melt them, they will change into liquid form, mix them, right? Then when you cool the solution of these two molten metals, they will form alloys, right? And how alloys are formed at atomic level, we'll see that today, right? So before these two things, let's just recall, we have studied in solid state physical chemistry about crystal lattice. And what is a crystal lattice? Crystal lattice shows us the arrangement of particles in a solid, right, in 3 dimensions, right? How particles of a solid are arranged in 3 dimensions, right? That's your crystal lattice, right? And so let's just draw it. Like we know, iron is a metal, it's a solid, right? So how particles in iron are arranged in 3 dimensions, that will be your crystal lattice of iron. So if this is your crystal lattice, right, and this will tell you, it's suppose these particles are arranged this way, right? This is how particles are arranged, right? Now these are atoms, say, of iron. Let's talk about interstitial compounds first. Interstitial compounds, how are these formed? If you look at this crystal lattice, they have space, right? This crystal lattice has space between, you can see this, right? There is space between these constituent particles, right? Now there are some small elements, right? Small elements like carbon, hydrogen, nitrogen, boron, right? These are very small compared to the size of these metal atoms. This metal atom is big, these are small. Nitrogen, hydrogen, carbon, all these are very small. So what they can do is they can take up these empty positions, right? If these elements, say carbon, if this is iron, we know that we have steel and stainless steel, right, which is made from iron and carbon. So when you mix carbon to iron, it becomes tough, right? It becomes very hard, right? How it becomes hard, right? You'll see it over here. So if you take carbon, add it to iron, right, it fills up the spaces, the empty spaces. These empty spaces are known as interstices. These are vacant spaces. Vacant spaces in crystal lattice between constituent particles. Vacant spaces, or we also call it as empty spaces, or we also call it as interstices, right? Now these vacant spaces between constituent particles, right, vacant spaces would be taken by these small atoms, right? These small atoms of carbon, say when we mix carbon with iron, right? So when these are known as interstitial compounds, when these empty spaces would be taken or occupied by these small elements like carbon, the resulting compound would be your interstitial compound, right? We call these as interstitial compound. Now since you are adding these small elements to these metals like iron, it basically does not change the chemical properties of the metals, right, of pure metal. But what it does is, because we know that solids are hard because their constituent particles are very close to one another, like this, right? That is why they are hard. Now what you are doing is, but this hard metal still have some empty spaces. These are empty spaces. Now what you are doing is, by forming these interstitial compound, you are filling up these empty or vacant or interstices with these small elements like carbon, hydrogen, nitrogen. So if you fill up these spaces, right, with these small elements, or if these small elements will occupy these empty spaces, the resulting thing would become more hard, right? It would become more hard, right? It will become more hard. That is why steel is harder, right, than iron, right? Because it has impurity of carbon mixed with it, right? I hope this is clear, right? So steel and cast iron are examples of interstitial compounds, right, of iron formed with carbon, right? You have done this in the metallurgy of iron, steel and cast iron. Steel and cast iron that are formed by mixing carbon in iron, right? In molten iron you add carbon, it will form steel and cast iron, right, which are hard compared to pure iron, right? Because what happens is, when you add carbon to iron, it will fill up these empty spaces. When you fill up these empty spaces, even the very less empty spaces that we have in case of metals, that are also gone, right? Now all these particles are more close to one another, right, which will result into more harder metal or more harder substance that has resulted by adding these small elements to the metals, right? So they have high melting points, they will have high melting points, right, because they are harder, so now they will have high melting points, right? And they exhibit conductivity similar, and it will not affect their conductivity, electrical conductivity. It would be same as the original element like iron, right? And melting points will increase, like I said, right? So I think this is clear. What are interstitial compounds? That have resulted by adding impurities to, or adding these small by adding these elements that have small size atoms to the metals, right? When you add these, because they are small, so they can occupy these spaces, empty spaces, resulting into a more hard substance, right? And steel and cast iron are examples. I hope this is clear. Now let's talk about alloys. Alloys are basically solid solutions, like iron, right, and chromium. They can, right, or manganese. Iron can form alloys with chromium or manganese. How it can form alloys, right? What we do is, you melt iron, right, melt chromium, right, then add and mix the molten iron and chromium, right? Mix molten iron and chromium, right? When you mix molten iron and chromium and then allow to cool them, right? Cool it, it will solidify. Since you have mixed both these metals in molten state, right? And when you have cooled them, it solidifies, right, and will form an alloy, right, which is a mixture of now iron and chromium, right? So how come iron and chromium can mix, right? If you look at these, if this is your iron, right, and if this is your chromium, this is your iron, say, right, and this is your chromium, right? The size of their particles, these atoms or particles, are same, right? Now because the size of their particles are same, chromium can replace iron and iron can replace chromium in the crystal lattice, right? Since they can replace one another, so say if I replace here 3 particles with chromium. So this is your alloy, right? And why they can replace? Because of their small size. Because of their same size, right? So here particles of one transition metal can replace particles of other transition metal. Right? Due to their same size. Due to their same size. This is the reason, right? Since they can replace one another's particle, so they will form this kind of solution, a new solid that will have constituent particles of iron and chromium both, or whatever solid solution you are making from whichever metals. I hope this is clear, right? So the reason that they can form alloys, transition metals can form alloys, is because of their same size, right? Because they have same size, so they can replace one another, right, to form solid solutions. I hope this is clear. Thanks.